What if a quiet scientific paper, posted online with almost no public attention, ended up challenging the official interpretation of one of the most mysterious objects currently moving through our solar system? On March 3, 2026, a technical research paper appeared on the scientific preprint server ArXiv. It was written by three researchers, Federico Spada, Marata Krokowska, and Luke Dons, and at first glance, it looked like a typical study in orbital mechanics, the kind of document that normally circulates quietly among specialists without attracting global attention. But the following morning, something unusual happened. Avi Loeb, the former chair of astronomy at Harvard University, read the paper and published a public response. His opening statement was calm but unmistakably direct. He wrote that the conclusions in this new analysis do not match the official report released by NASA. And then he added a sentence that scientists almost never say publicly about a major space agency. Official statements from NASA can be wrong because science is ultimately a process of learning. When someone with Loeb's credentials makes that statement openly, it immediately signals that something important is happening. The disagreement is not about a minor measurement error or a small calibration adjustment. It concerns a fundamental question about the strange object known as 3I, Atlas. Specifically, it involves the direction of the object's non-gravitational acceleration, the subtle force that is slightly changing its trajectory as it moves through the solar system. According to NASA's current model, the force pushing on the object is directed away from the Sunday, but the new paper suggests something different. The researchers claim the object is also being pushed sideways along its path through space. At first glance, this may sound like a technical detail, but in orbital physics it makes a major difference. A push directly away from the Sun fits the behavior we normally expect from a natural comet. A sideways push requires a more complicated explanation. To understand why this matters, we have to start with the basic idea of non-gravitational acceleration. In space, the motion of most objects is governed by gravity. The Sun pulls on planets, asteroids, and comets, and those bodies also feel weaker gravitational influences from other planets. Using the laws of celestial mechanics, scientists can calculate these gravitational forces with astonishing precision. If we know the position and velocity of an object today, we can usually predict exactly where it will be years or even centuries in the future. But comets behave slightly differently. When a comet approaches the Sun, the heat causes frozen gases inside the nucleus to sublimate. Instead of melting into liquid, the ice turns directly into gas and escapes into space. As the gas streams outward from the surface, it acts like the exhaust from a tiny rocket engine. The escaping material pushes the comet in the opposite direction. This additional force is extremely small, but over long periods of time, it becomes measurable. Astronomers call this effect non-gravitational acceleration because it comes from the comet's own activity rather than from gravity itself. The strength of this push is tiny. In the recent analysis by Spada and his colleagues, the acceleration is estimated to be roughly 1 micrometer per second squared at the distance of Earth from the Sunday. That number is almost unimaginably small. It represents only a fraction of the width of a human hair of velocity change per second. For most everyday purposes, it would be completely negligible. But in orbital mechanics, where even a tiny deviation can accumulate over months or years, it becomes extremely important. Back in 1973, astronomers developed a standard mathematical framework for describing this effect. The model divides non-gravitational acceleration into three components. The first component, called A1, represents acceleration directed radially, either toward or away from the Sunday. The second component, A2, represents acceleration along the direction the object is traveling in its orbit. This is known as the transverse component. The third component, A3, points perpendicular to the orbital plane. For most comets, the strongest effect is the radial component. The side of the comet facing the Sun becomes warmer, causing gas to escape from that surface. The reaction force pushes the nucleus away from the Sun, producing a predominantly radial acceleration. That pattern is exactly what astronomers expect from a natural comet whose activity is driven by solar heating. This is also the conclusion currently reported in the official orbital solution maintained by NASA Jet Propulsion Laboratory. According to their analysis, the The radial component A1 is roughly 5 times larger than the transverse component A2. In other words, the object appears to be receiving a strong push directly away from the Sun with only a smaller sideways influence. That interpretation fits comfortably within the normal physics of cometary outgassing. The new paper, however, paints a different picture. Instead of a dominant radial force, the researchers found that the radial and sideways components are nearly equal in magnitude. If that result is correct, the object is not simply being pushed outward by sunlight heating its surface. It is also being accelerated significantly along the direction of its motion. This difference may sound subtle, but it changes the entire physical interpretation of what is happening. A predominantly radial push fits neatly into our understanding of natural comet behavior. A sideways acceleration of similar strength requires a specific geometric configuration of gas jets or some other mechanism that directs the thrust along the orbital path. So before jumping to conclusions, we need to examine exactly how these measurements were made and why the two analyses reached different answers. The official solution, produced by NASA's Orbital Dynamics team, was based on hundreds of carefully vetted observations. Each measurement of the object's position was processed using strict quality controls before being included in the final calculation. The new study takes a different approach. Instead of relying on a smaller curated dataset, the researchers analyzed thousands of astrometric observations covering a longer time span. Their dataset includes measurements taken both before and after the object passed its closest point to the Sun. That expanded observational arc may reveal subtle changes in the object's activity that were not fully captured in the earlier model. In other words, two serious scientific analyses are looking at the same object but using different methods and different amounts of data. And those choices lead them to two different conclusions about how the object is accelerating in space. To understand why the sideways component matters so much and how it might be connected to a strange pattern of jets observed around the object, we need to examine what the new study actually discovered and why it has caught the attention of researchers around the world. And the deeper we look into the details of that analysis, the more the mystery surrounding 3I Atlas begins to grow. To understand why the new analysis has created so much discussion among astronomers, we need to look closely at what the researchers actually discovered when they re-examined the motion of 3I Atlas. The official orbital solution maintained by NASA Jet Propulsion Laboratory is based on 782 carefully selected astrometric observations. These measurements were processed and filtered using strict quality standards before being used to calculate the object's trajectory. That approach has been refined over decades and works extremely well for the vast majority of comets and asteroids moving through our solar system. In the NASA model, the result is clear. The radial component of non-gravitational acceleration, known as A1, dominates the motion. It is roughly 5 times stronger than the transverse component A2. Physically, that means the main push acting on the object is directed away from the Sun, exactly what scientists would expect if sunlight is heating the comet's surface and causing gas to escape from the Sun-facing side. In this interpretation, the sideways acceleration exists but plays only a minor role. The new study by Federico Spada and his colleagues approached the problem differently. Instead of using a smaller, highly filtered set of observations, they examined a much larger dataset, 7,388 astrometric measurements, collected between May 8, 2025 and February 19, 2026. That is more than 10 times the number of observations used in the official solution. More importantly, this expanded dataset includes measurements taken after the object passed its closest point to the Sun, a phase known as post-perihelion. This difference in data coverage turns out to be crucial. Before perihelion, a comet is heating up as it approaches the Sun, and its activity gradually increases. After perihelion, however, the behavior can change dramatically. Jets may shift location, new vents may become active, and the pattern of gas emission can evolve as the nucleus rotates and cools. By including observations from both phases of the orbit, the researchers hope to capture a more complete picture of how the object's activity affects its motion. When they ran their orbital calculations using the full dataset, the result was surprising. The radial component A1 remained strong and consistent with previous estimates, The normal component A3, which measures acceleration perpendicular to the orbital plane, also showed values that were broadly consistent with expectations, but the transverse component A2 behaved very differently. Instead of being 5 times smaller than A1, the sideways acceleration turned out to be almost the same magnitude. In other words, the object appears to be receiving a push not only away from the Sun, but also strongly along the direction of its orbital motion. The forces acting on the object are not dominated by one direction. They are roughly balanced between radial and transverse acceleration. This is not a minor adjustment to an existing model. It is a fundamental shift in how the physics of the object is interpreted. In the NASA model, sunlight heating the comet naturally explains the acceleration. In the new analysis, the pattern of forces requires a more complex explanation, and this is exactly the point highlighted by Avi Loeb when he summarized the study in his response. According to Loeb's interpretation, the new calculations suggest that 3I, Atlas, is being pushed sideways rather than simply outward from the Sunday. That distinction matters because the mechanism responsible for producing such a force must be capable of directing gas in a very specific way. In a typical comet, gas escapes mostly from the sunlit side, which naturally produces a radial push. Generating a large transverse acceleration requires jets that are oriented differently relative to the object's spin and orbit. One possible explanation involves the geometry of the comet's rotation axis. If the spin axis happens to point nearly toward the Sun, then the most active gas vents could be located at high latitudes relative to the orbital plane. As the nucleus rotates, these vents would release material in directions that include a significant sideways component. Over time, the combined effect of these jets could produce the transverse acceleration measured in the new study. Interestingly, this scenario connects directly to another observation that has been puzzling researchers for months. High-resolution images captured by the Hubble Space Telescope revealed something unusual in the structure of the object's coma. After removing the bright, symmetric glow surrounding the nucleus, astronomers detected 3 distinct jets of gas and dust emerging from the object. These jets were not randomly distributed. They appeared to be spaced at nearly perfect intervals of 120 degrees around the nucleus. Even more intriguing, the jets seemed to wobble as the object rotated, completing a full cycle roughly every 7.1 hours. This periodic motion suggests the jets are anchored to specific regions on the rotating surface of the nucleus. In addition to these 3 jets, the images also revealed a 4th feature known as an anti-tail, pointing toward the Sunday. When researchers combined these observations with the new orbital analysis, an interesting picture began to emerge. If the spin axis of the object is indeed oriented close to the direction of the Sun, then the 3 jets spaced 120 degrees apart could be positioned at high latitudes. In that configuration, the gas escaping from those vents would naturally produce both radial and sideways thrust. The combined force from 3 evenly spaced jets could therefore generate exactly the kind of acceleration pattern reported in the new study, a radial push away from the Sun and a transverse push along the object's orbit with comparable strength. From a purely physical standpoint, this explanation is internally consistent. The geometry of the jets aligns with the direction of the measured acceleration. 2 independent sets of observations, the imaging data and the orbital calculations appear to support the same interpretation. However, the precise symmetry of those jets still raises questions. Natural cometary activity tends to be messy and irregular. Jets often appear and disappear unpredictably as different regions of the surface heat up. They rarely maintain perfect geometric spacing for long periods of time. Yet in this case, the jets appear separated by almost exactly 120 degrees and have persisted over multiple observations spanning several months. That symmetry is what Loeb described as enigmatic. It does not automatically imply anything artificial, but it does mean the configuration is unusual enough to deserve careful examination. For now, scientists are continuing to analyze the available data while preparing for the next critical moment in the object's journey through the solar system. Because in just a few days, this mysterious visitor will experience a close encounter with one of the most powerful gravitational forces in our planetary neighborhood. And that encounter may provide the decisive measurements needed to determine which model of 3I, Atlas, is actually correct. That decisive moment is approaching quickly, and it may provide the clearest test yet of the competing explanations for the motion of 3I Atlas. In just a matter of days, the object will pass near the largest planet in our solar system, Jupiter. This encounter is not simply another point along its path. It is a rare opportunity for astronomers to measure the object's trajectory with extraordinary precision and determine which model of its motion is actually correct. When a small body passes close to a massive planet, the planet's gravity alters the object's trajectory in a predictable way. The amount of deflection depends on a few factors that are already known very accurately: the mass of the planet, the geometry of the encounter, and the exact position and velocity of the object as it approaches. Because Jupiter's mass is measured with extreme precision, any change in the object's path during the flyby can be calculated very reliably using the laws of gravity. This is where the disagreement between the two orbital models becomes crucial. The predictions produced by the official analysis from the NASA Jet Propulsion Laboratory and the calculations presented in the new study begin with slightly different assumptions about the object's acceleration before the encounter. Those differences may seem small now, but when projected forward to the moment of the flyby, they lead to slightly different predictions for the object's position and motion. After the encounter occurs, astronomers around the world will measure the object's new trajectory using high-precision astrometry. By comparing the observed path with the predictions made by each model, scientists will be able to determine which one more accurately describes reality. In other words, Jupiter's gravity will effectively act as a natural experiment, testing our understanding of how the object has been accelerating. The encounter will also extend the observational timeline of the object. Each new measurement adds another data point to the orbital arc, allowing researchers to refine their calculations. As more observations accumulate after the flyby, the uncertainties in the transverse component of the acceleration, the controversial A2 parameter, should gradually decrease. There is another factor that could make the upcoming period especially informative. When comets pass through strong gravitational environments, the tidal forces acting on their nuclei can sometimes trigger bursts of activity. If the gravitational stress from Jupiter causes new outgassing events, those eruptions could slightly alter the object's motion and reveal additional details about how its jets operate. Such outbursts are particularly interesting in this case because the composition of the escaping gas appears unusual compared with typical comets. Observations have suggested that carbon dioxide may dominate the activity of 3I Atlas rather than water vapor, which is the more common driver of cometary jets within our solar system. If additional activity occurs during or after the encounter, scientists may gain a clearer picture of how that composition affects the forces acting on the nucleus. Stepping back from the technical details, the broader significance of this debate becomes clearer. What we are seeing is not a clash between established science and speculation. Instead, it is a genuine scientific disagreement between different groups of researchers analyzing the same object with different datasets and methods. Both sides are using rigorous approaches, and both are attempting to explain the same physical measurements. Situations like this are actually a normal part of scientific progress. Early models are often based on limited observations. As new data arrives, researchers revisit those models and sometimes discover that the initial interpretation needs to be revised. That process of refinement is exactly what keeps science moving forward. The current discussion also highlights how institutional authority interacts with independent research. Major organizations like NASA have developed extremely reliable procedures for calculating the orbits of thousands of small bodies in our solar system. Those methods are optimized for the typical behavior of asteroids and comets that originate within our planetary system. However, objects that come from outside our solar neighborhood, interstellar visitors, may not always behave exactly like the bodies those procedures were designed to analyze. If 3I Atlas truly originated beyond the boundaries of the solar system, its composition, structure, and activity could differ in subtle ways from the comets scientists have studied for decades. That possibility is part of the reason this object has attracted so much attention. Since mid-2025, researchers including Avi Loeb have been cataloging a growing list of unusual properties associated with it. Among those features are the unexpected jet geometry revealed in images from the Hubble Space Telescope, the unusually high ratio of carbon dioxide to water vapor in its emissions, and the asymmetric pattern of activity before and after its closest approach to the Sun. Each of these characteristics can still be explained within known natural processes, but together they form a collection of observations that sits near the edge of what standard cometary physics typically predicts. The new analysis of non-gravitational acceleration adds another layer to that picture by suggesting that the sideways component of the force acting on the object may be much larger than previously believed. Importantly, none of this proves that the object is artificial or technologically driven. Scientists involved in the discussion have been careful to avoid making such claims. Instead, the focus remains on understanding the physical mechanisms that could produce the observations currently available. That is why the upcoming gravitational encounter with Jupiter is so important. It will provide fresh measurements, extend the data record, and potentially resolve the disagreement between the competing models. Within weeks of the flyby, updated orbital solutions will likely appear, incorporating the new observations and revealing whether the transverse acceleration really is comparable to the radial component. Until then, the story of 3I, Atlas remains unfinished. A quiet research paper posted on March 3, 2026 introduced a new interpretation of the object's motion. 2 days later, a prominent astrophysicist publicly acknowledged that even official institutional analyses can sometimes be revised as new information emerges. Now, the next chapter of the investigation is about to unfold as the object approaches the strongest gravitational field it will encounter during its passage through the solar system. If you want to follow how this mystery develops as new data arrives after the Jupiter flyby, make sure you stay connected with the channel. Like the video if you found this analysis interesting, share it with someone who enjoys space science and cosmic mysteries, and subscribe so you don't miss the next update, because the story of 3I, Atlas is still unfolding, and the most revealing discoveries may still be ahead.